There is an iron axe head in a museum vault that was made around 1200, 800 years old. Get it? Look at the blade. The top has a black patina, but the metal underneath is sturdy and strong, with no significant pits or signs of structural degradation. Now, go outdoors to your garden shed. You bought a steel axe 2 years ago. There is already orange rust on the head. You will toss it away after 5 years, since it will be so rusty. How can this be? How can something built with simple tools in a clay furnace live longer than sophisticated steel that was carefully constructed? The answer is not magic. It's chemistry. We gave up our understanding of iron for convenience and an accident. Before we go into this long-lost science, put "built to last" in the comments if you think we've lost something important in our quest for cheap throwaway tools. I want to know whether this makes sense to you. Stop saying that right now. Part 1. The challenge of modern rust. We need to know what modern steel actually is before we can grasp why Amish iron doesn't rust. When you buy a tool today, you are getting what metallurgists call mild steel. It has about 0.25% carbon, no slag, and no phosphorus. We call this a step forward. Amish wrought iron was very different in a lot of ways. It had barely 0.05% carbon and up to 2% slag, which are the glassy impurities that are left over after smelting. It also had phosphorus in it, which originated from the ore and may be as high as 0.25%. Steel manufacture today purposely gets rid of both the phosphorus and the slag. Why? Because they make it tougher to work with steel in factories. Steel that doesn't have any slag in it can be rolled into sheets more quickly. Steel that doesn't have phosphorus in it is easier to weld together on assembly lines. We made things faster to make, not stronger. But we didn't grasp this till lately. Those flaws weren't problems, they were features. When modern steel rusts, the corrosion goes straight down. A little bit of wetness hits the surface. Iron and oxygen react with each other. The rust grows. That rust is full of holes, which means it holds more moisture, which makes more rust. Like roots following flaws in concrete, the corrosion digs deeper along the grain limits of the metal. A little fracture in contemporary steel lets rust get in. It can't be stopped. In a few months, surface rust can turn into structural damage. Slag stringers were Amish wrought iron's secret weapon. As the blacksmith hammered the bloom of iron, small strands of crystalline slag spread across the metal. It appears like wood grain under a microscope, with hundreds of tiny glass threads flowing through the iron matrix. When rust began to form on wrought iron, it would contact one of these slag barriers. The glass fiber would slow down the corrosion, making it spread sideways instead of going deep. The end result is an axe head that stops corroding and creates a protective patina instead of collapsing into orange powder. Hit the like button if you are learning something useful here. It doesn't cost you anything, but it helps get this information to others who need to hear it. A quick tap, and then we move on. Part 2. Phosphorus's unintentional genius. Amish blacksmiths didn't know anything about chemistry. They didn't know what phosphorus was, but they did know which rocks formed the best iron. Iron ore evolved naturally in bogs in marshy locations all across Europe. It was easy to collect this bog iron ore. You could almost rake it off the ground. But it contained something special, a lot of phosphorus. That phosphorus stayed in the metal after bog iron was melted down. And when that iron rich in phosphorus progressively rusted over the years, something amazing happened. The phosphorus helped build a thick, stable layer of protective oxides on the surface. This layer kept moisture and oxygen from getting to the metal, which slowed the rusting process by a lot. This was a fortuitous accident, an impurity in the ore that was good for it. The smiths didn't know why bog iron worked better, they just knew it worked. The most impressive example of this effect is in Delhi, India. The iron pillar in Delhi is more than 1,600 years old. It is almost completely rust-free and weighs more over 6 tons. Scientists were confused for decades. How could iron last that long? The answer was found by modern metallurgical analysis. The pillar was made of iron with a lot of phosphorus in it, which slowly corroded over hundreds of years. At the interface between the metal oxide and the water, a thin layer of crystalline iron hydrogen phosphate hydrate developed. This layer is quite stable and doesn't have any holes in it. It works like a ceramic coating. It doesn't let moisture in. After making this protective coating, the pillar stopped rusting. European blacksmiths were making the same thing happen, but on a lesser scale. We mined deep underground for pure iron ore every time they made a tool out of phosphorus-rich bog iron or contemporary steel. Then, on purpose, we took out phosphorus throughout the refining process. We gave up corrosion resistance in exchange for easier production, but the phosphorus benefit wasn't just for European bogs. In the Amish community, some places became famous for their iron, not just because they were better at their jobs, but also because the land was different there. Amish blacksmiths in Toledo, Spain, made blades so famous that knights went all over Europe to get them. The ore held the secret. Nickel and chromium are naturally present in the iron deposits around Toledo. We put these components in modern stainless steel on purpose, but they were accidents of geology. Toledo steel was less likely to rust than iron from other places because the mountain itself was an alloy. Smiths made wood steel in southern India, which Europeans termed Damascus steel. Recent studies have shown something amazing about these old blades. They have carbon nanotubes in them, which are so advanced that materials scientists didn't find them until the 1990s. The Amish blacksmiths didn't know they were making nanotechnology. The gradual cooling of their crucible technique, along with trace elements in the ore, accidentally put these molecular configurations together. Amish trading routes moved high-quality iron blooms from one continent to another. A smith in England would pay a month's salary for a bloom of Swedish iron that is known for being pure and easy to work with. Arabian traders brought Indian woods cakes to Damascus, where they were turned into famous swords. The idea was the same everywhere. Beneficial impurities from local geology, along with procedures that kept them rather than eliminating them, made materials with qualities that are hard for us to copy today. We are not smarter than the smiths in the Amish community. We just decided to optimize for various purposes. Part 3. The bloomer's edge. The technique that made this better iron was very simple. The blooming furnace was a clay and stone chimney that was only as tall as a person. There were layers of charcoal and iron ore layered on top of each other. Bellows pushed air through pipes at the bottom. The trick was controlling the temperature, or rather not being able to. A bloomer worked at a temperature of about 1200 degrees C. It was hot enough to chemically break down the ore, but not hot enough to melt the iron. At 1538 degrees C, iron melts. The blooming never got to that point. Instead, everything went slowly and messily. The burning charcoal made carbon monoxide gas. This gas took oxygen out of the iron ore, leaving behind bits of pure iron. But the ore's stony impurities, such as silica and other minerals, did melt. They made a glittering slag that dripped down through the furnace. The solid iron particles sank into this molten slag bath and formed a spongy mass at the bottom termed a bloom. The smith would open the furnace after hours of effort and take out this glowing lump. It looked more like rock from a volcano than metal. This is where the magic happened. As the iron particles formed, they were surrounded by burning charcoal for hours, which made them take in carbon unevenly. Some places absorbed relatively little, thus they stayed as soft wrought iron. Some places absorbed more and turned into steel by mistake, and there were pieces of that protecting slag all over the place. Cold rolling is how modern steel is made. At room temperature, rollers push steel bars through them, rapidly and easily forming them. That wasn't an option for Amish blacksmiths. They had to work with hot iron. The bloom was heated up again in the forge and hammered over and over. This hot work did something really important. It got rid of some of the slag, yes, but it also compacted and lined up the slag that was left over, turning it into those little fiber networks. With each blow of the hammer, the iron particles stuck together more strongly. Every time it was reheated, carbon might move around again. The continual effort got rid of internal strains and microfissures. The smith wasn't merely sculpting the metal. With each hit, he was radically changing the structure of the inside. It took a while. It could take 3 days of heating and hammering a single axe head, over and over again. A factory nowadays can stamp out the same shape in 3 minutes. We chose to go fast. They made it last. Part 3.5. The Economics of Staying the Same. To comprehend the exceptional rust resistance of Amish iron, it is essential to grasp its significance. It wasn't just a thing. It was a lot of time, skill, and worth. Those 3 days to make one axe head, work of a great artisan for 3 days. In Amish England, a good axe might cost as much as a month's worth of a laborer's pay. A sword might be worth 6 months' worth of pay. They weren't things that were bought. They were investments that were designed to endure a lifetime and then be passed on. This made an economic reality that we have utterly lost. You didn't throw away your grandfather's hammer just because it had some rust on it. It cost as much as a month's worth of food for your family. You kept it up. You put oil on it. You put it away the right way. Wills listed tools that were expensive. Inheritance issues fought over them, and owners designated them with their own emblem. Before they could call themselves journeymen, Amish blacksmiths had to work as apprentices for 7 years. It could take another 7 years for a smith to become a master and get authorization to operate their own forge. This was not a romantic custom. It was necessary for the economy. A tool that was poorly built and broke may kill someone. If a plow breaks during planting season, people could starve. The Amish guild system made sure of this attribute by being very simple. If you didn't do a good job, you were kicked out of the guild. If you weren't a member of a guild, you couldn't legally sell your work. The guild's name was more important than any one smith, so quality was not an option. We suppose that Amish iron's rust resistance is due to better technique, but technique alone doesn't mean much until there are economic pressures to keep up standards. They manufactured iron that lasted because creating iron that broke was a bad idea for business. Axe from a hardware shop costs $15 today. You get a new one if it rusts out in 2 years. The maker doesn't get in trouble. There's no guild that can kick them out. The economic incentive has turned upside down. There is no conspiracy behind planned obsolescence. It is just more profitable than being permanent. Part 4. We forgot about the charm of maintenance. Amish blacksmiths knew something that we have forgotten. New iron needs to be treated. The smith would do something we may call seasoning after shaping a tool into its final form, but they didn't use that phrase. The finished item would be heated until it turned dull red, and then it would be rubbed with linseed oil or animal fat while it was still hot. The heat made the oil polymerize, which made a hard, thin layer stick to the metal surface. This layer wasn't paint. It was a coating of molecules that kept moisture and oxygen from getting to the iron. You still season a cast iron pan the same manner. But steel tools made today don't come with anything. A thin layer of machine oil that comes off the first time it rains. No one teaches you how to season your tools since modern steel is meant to be thrown away. The iron that the Amish used all the time had another benefit. There would be a black, stable patina on the surface. This was not rust that caused damage. It was magnetite, a type of iron oxide that is heavy and protects. The patina stayed preserved because it was used often. The oil from people's hands, the friction of work, and the regular exposure to air without long periods of dampness all helped keep a protective surface layer. Tools that were kept dry and used a lot could last for many years. The grandson would get his grandfather's hammer, which was still in good shape. We stopped doing these things not because they didn't work, but because they needed maintenance. Modern tools are made to be replaced, not fixed. You might wonder why we don't create Amish iron that way now if it was so much better in resisting rust. The answer is not ignorance, but economics. A bloomer furnace can make about 50 pounds of iron every day. A contemporary blast furnace makes hundreds of tons. It's not simply the size that makes a difference, it is power. The temperature in a blast furnace is more than 1,500 degrees Celsius. Iron melts all the way through. Liquid waste is used to skim off the slag. The end product is pig iron that is melted and has a lot of carbon in it. It needs to be refined into steel in a different step. Quick, effective, and always the same. But there is a price to pay for that steadiness. You can't regulate how the tiny slag stringers are spread out in liquid metal. You can't mistakenly keep good phosphorus while getting rid of bad sulfur. The blooming method took a long time because it worked at the edge of iron's change in a very small temperature range where solid-state chemistry could do its magic. We gave up the enchantment in exchange for the power to create 1 billion fence posts every year. They're cheap, but most will rust away in 10 years. The secret of the composite blade is in Section 5. Every blossom from the bloomer had a messy mix of elements for the Amish smiths: soft wrought iron, firm steel, and a protective slug. Someone who isn't very good at their job might regard this as a problem. A master thought it was a chance. The smith could read the metal. He could tell how much carbon was in a piece by hitting it against a grinding wheel and watching the sparks fly. Soft iron makes lengthy, slow orange sparks. High-carbon steel explodes in bright white bursts. The smith would use this sensory information to sort the bloom. High-carbon chunks were quite valuable. They would make the edge sharp. The softer wrought iron, which is strong and can absorb shocks, would make up the body and spine of a blade. They were forge-welded together and then heated until they were white-hot. Their surfaces would start to melt. A couple hits with a hammer made them stick together for good. The end product was a blade with a strong edge that stayed sharp and a flexible core that could take hits without breaking. This composite structure, with its hard edge and robust body, was not just one material trying to be two things. It was made of two things, each of which did what it did best. Some smiths went even further and made pattern-welded blades by twisting bars of iron and steel together before forging them. The results exhibited a pattern on the surface that looked like water. It was both beautiful and useful. But this is what matters when it comes to rust resistance. Those forge welds made more places for slag stringers to build protective networks. A pattern-welded blade was not only sturdy, but it also had a coating that kept it from rusting from the inside out. Part 6. The Science Behind the Magic. Amish Alchemy That Really Worked. You can find recipes that sound like witchcraft in Amish blacksmithing books. Theophilus, a German monk from the 12th century, claimed in 1125 that instruments are tempered harder in the urine of a tiny red-headed youngster than in regular water. Other Amish writings called for even weirder mixtures. One recipe asked for 1 part white radish, 1 part horseradish, 1 part earthworm larvae, and 1 part buck's blood when the buck is in rut. Another suggested using clarified honey, fresh heifer goat urine, alum, borax, olive oil, and salt to make the best drink to quench your thirst. Historians have called these things superstitions for hundreds of years. Folklore is the magical ideas of people who didn't know much about chemistry. After that, metallurgists from today chose to test them. The outcomes were not what I expected. A lot of the strange quenchants didn't work. Blood, even though it was famous for manufacturing swords, cooled steel too slowly to harden it correctly. Milk was just as useless. The romantic idea of a sword soaked in the blood of adversaries? Just a fantasy. But two drinks worked really nicely: urine and water. Why pee? The answer is simple chemistry that sounds supernatural. Urea in urine breaks degraded into ammonia and carbon dioxide. But more crucially, it has mineral salts like salt, sodium chloride, potassium, and others. When you put red-hot steel into clean water, something bad happens. There is an instant coating of vapor around the metal. This steam envelope keeps the heat in and slows down the cooling process. The steel won't harden right if it cools too slowly. This problem can be remedied with salt. The particles in salted water, or urine, break up the steam layer before it can fully form. The liquid stays in direct contact with the hot metal. It cools down faster. It works to harden. Amish blacksmiths learned this by trying different things. They didn't know about steam envelopes or how to start boiling. They just knew that soaking instruments in urine or brine made them tougher than soaking them in pure water. So they put that useful information in mystical terms. The phrase "add salt to your quench" possibly meant the urine of a red-headed boy. The complicated recipes that call for honey, herbs, and animal parts, those extra minerals and organic molecules made it even harder for steam to develop. The smiths were doing experiments in material science, one quench at a time, and writing down what worked without knowing why. Amish blacksmiths did another important step after hardening steel in a quench: tempering. They would gradually reheat the blade and watch colors spread across the polished surface. Pale straw yellow, deep copper, peacock blue, and purple are some of the colors. These hues were not for adornment. The oxide layers that built up on the steel surface made them an incredibly accurate way to measure temperature. There was a different temperature for each color, and each temperature changed the qualities of the substance. Steel was great for cutting edges when it was straw yellow at about 230 degrees Celsius. Bronze that was about 255 was perfect for swords and springs that needed to be flexible. Blue, about 300 degrees, made implements that could take hits without breaking. The smith would heat the blade until it turned the right color, then cool it down very away to keep that exact microstructure. He was able to change the shape of steel crystals just by looking at them and knowing what to do. We still utilize color tempering today, but smiths who worked with medieval metals came up with this method not by comprehending it, but by watching it happen over and over. They saw that a sword that was heated to bronze color held up better in battle than one that was heated to blue hue. So they wrote down that information in guild secrets and the way masters and apprentices worked together. The magical language kept important commercial secrets safe. But there was true tested repeatable science behind every mention of the four elements or the right phase of the moon. We needed 3 more hundred years of chemistry to figure out what they already knew how to do. The secret was what caused the failure. Amish iron wasn't ideal. It wasn't pure. It wasn't always the same. According to all modern metallurgical standards, it was bad material. But a knife made in 1300 can still cut. An axe from 1150 can still cut wood. Not because they are flawless, but because they are not. The trash that modern refineries throw away is microscopic armor. The phosphorus that contemporary techniques get rid of is a contaminant used to stop rust. The bloomery technique took a long time and a lot of work to produce an interior structure that liquid metal blast furnaces can't copy. We didn't lose this information because of a disaster in the Dark Ages. We left it on purpose. We picked quantity over quality, convenience over quality, and inexpensive over long-lasting. The Amish blacksmith's genius was not in getting rid of flaws. It was in recognizing that imperfection might be strength if it was handled right. The early blacksmiths standing in front of their clay furnaces knew something deep. They knew how to read iron's soul. They knew which rocks to pick up from the marsh. They recognized that heating and hammering something over and over again made something that no factory can make in large quantities. They made tools that would last longer than the person who made them. We make tools that are supposed to be replaced. That isn't progress. You can choose that. Every rusty fence post, every corroded garden equipment, and every axe from the hardware store that only lasts 2 seasons is a reminder of what we chose. Make sure you are subscribed if this made you realize how much we have lost because of cheap manufacturing. We're finding more old technology that makes new solutions look bad. If you want to see us talk about more things like this, hit that like button. What other old technologies should we look at more closely? Leave your ideas in the comments. And don't forget that every time you buy a tool, you're voting with your money. Buy once and cry, or buy cheap and buy twice and fill landfills with rust. Thanks for watching.